Very hard. Okay, please take the picture of the whole class. Okay, in this class we talk about the derivation of virtual work principle. We first start from the equation of equilibrium. We have in the general case we have three-dimensional deformable body. So we have the equilibrium equation in three directions: x direction, y direction, and z direction. So basically, we have three equations for equilibrium state. And then the special point of the virtual work principle is that we take these three equations as a vector. We put this as F1, put this equation as F2, and put this equation as F3. Okay, we turn these three equations into a vector with three components. Okay, and then we assign an arbitrary vector G. G is a vector function. Okay, we perform the inner product between F vector and G vector, such that we get a scalar function. See, originally we have three scalar functions, 1, 2, 3, and then we put this as a vector, and then we do the inner product with G vector to get a scalar function here. So by writing down these details, I want to tell the whole class that it is a very special mathematical skill. Okay, we have three equations, and we take these three equations into an inner product, okay, and turn it into a scalar function. So now we have only one equation remain here. So this is the starting point of the virtual work principle. Okay. Now, after we have writing all this, we can start to perform some mathematical transformation. Okay, we have this scalar equation come from the three equilibrium equation, and then we put this equation into an integral. Okay, we integrate the equation with the whole deformable body. So the domain of the integral, we can write it as D0. D is domain. Okay. So this is the domain for the integral. So here we basically are dealing with a volume integral. Now we try to turn this volume integral, a part of the volume integral, into the surface integral. Why we need to do this? Because we want to relate our mechanical property to the material or to the boundary loading on the surface, on the deformable body. So we need to turn this volume integral into the surface integral. Okay, but before this, we need to carry out some detailed derivation. Okay, we express it for this term. Okay, we write this term here and this term here, and then we use the basic formula of calculus to turn this term into two terms. Okay, here this term means that partial x j, we have two functions. A is g big G. B is GI here. And then this one is and this one is. So by writing in this way, you can understand that it is no big deal. It's like the easy formula come from the basic calculus formula. So we can turn this term into two terms separately, and then we can separate this volume integral with two parts here. This one we put this into let me do step by step. Okay, here this one. Okay, and then this. Okay, we put this into this and this into this, and then this into this. Okay, so we can separate the volume integral into two parts, and especially for this part, we can apply the divergence theorem here. By using the divergence theorem, we can turn the volume integral, see, to integrate with respect to the volume here, integrate with respect to the surface. We turn the volume integral into the surface integral by this step. This is a crucial step. Because we want to relate our physical property from the internal part of the body to the surface of the body. So by doing this, we finally can get the surface integral according to the divergence theorem. So this is a very important step for the derivation of virtual work principle. We try to turn our volume integral into a surface integral such that the external loading on the surface can be related to the integral here. So now finally we have this term. This is the external force. Okay, this is the external force, and this is the virtual displacement, and then this is the virtual work done by the external force. Okay, so this is a very important step. We start with the equilibrium equation. Now we end up with the external force on the surface. Okay, by this beautiful divergence theorem. Okay, this is the major part of the derivation of the virtual work principle, but we still have a lot of, I don't want to say minor details, we still have a lot of other important details. Okay, but this is a very important part. Okay. Now with this integral at hand, we try to understand the physical meaning now. This term is the virtual work done by the external force. This term is the virtual work done by the body force. And this term is the internal virtual energy created by this external force and body force. Okay, so we related the work to the internal energy by this formula. But these energy are virtual energy, and these work are virtual work. Okay, so with this formula at hand, we have basically the general form of the virtual work principle. See, in many textbooks, in the undergraduate level, we deal with the mechanics of material, of theory of structures, and in all these textbooks, the form of the virtual work principle is very simple because they only work for this for very special shape of the structures or bodies. But now, in this class, we divide the virtual principle in this way. We finally obtain a virtual principle which can be applied to arbitrary shape. Okay, so this form is more general than those you have learned before in the undergraduate textbook. Okay, let me ask you. 10 minutes already, or still? Already. Okay, so we can stop here. So thank you.